Okay. Anybody need time? More? We can start. If you are done. Done. Good. Everybody okay? Okay, we can slowly start. Yeah, let's see what we had last class. Of course, we are in random variables. I hope you know what is random variables now. Is a function that kind of map random events to a number. The idea is to mathematically model the world, probabilistic world or uncertain world. That's the reason of this class. We talked about some other factors to study these random variables. One of them was CDF, cumulative distributed function, and then derivative of that was probability density function. Density, this is not like probability, it's a density, probability density function. So about probability density function, we said this function, we call it lowercase f of x, is derivative of CDF, capital F. So because this CDF is always increasing, in continuous case is also continuous. That's why we can get derivative. So we also said this function, this PDF function, is not a probability, so can be bigger than 1. So we also mentioned that. And also we know is always bigger than 0. And the integral from minus infinity to infinity of this PDF is always 1. Okay. Even we went further. We said we can find probability of one interval using this PDF. So probability of x between a and b is equal to the integral between a and b, f of x, d of x. Okay? So as I asked also in your quiz, doesn't matter if you put this equal or not, because probability of x is equal to something in a continuous form is always 0. Yeah, this is pretty much what we learned last class. But we had one problem here last class. We said how this can be 1, how this integral can be 1 if we can have sometimes probability density function more than 1. The reason is the fact that there is a very little important difference between integral and summation. So I didn't consider this part last class. So integral between a and b, f of x, d of x, is equal to sum, but not normal sum, limit of sum, when delta x going to 0, f of x, delta x. So we didn't consider this multiplication. I said, oh, we are just adding them. How this can be bigger than 1? And add of many of that can be 1. The point is we didn't consider this delta x or d of x, delta x, that is multiplying to that and add together. We're going to see one example of this in next slide when I'm explaining continuous uniform distribution. But that's the reason that even though f of x is bigger than 1 sometimes, when we get integral, the integral is always 1. Okay? We're going to see that in one example, but I need to explain some stuff before that. Okay? So that's something that we had last class. But today we're going to talk about more family of continuous random variables, especially Gaussian, if we get chance. A uniform, we're going to talk about uniform, but not discrete form of uniform, continuous form of uniform. Exponential. Exponential are amazing because exponential and actually geometric are very close. You know, geometric and exponential are like limit of each other when they go to infinity. Anyway, we're going to talk about that, and also, of course, Gaussian. Let's see how much we can go deeper in Gaussian. Gaussian is amazing, and in this class, you can see application of that a lot and a lot. So let's talk about family of continuous random variables. We already know family of random variables. Family of random variables are the type of random variables that follow same mathematical formula, same mathematical form, same PDF, same actually discrete form, probability mass function in continuous probability distribution function. Same PDF, but different parameters. We have some parameters for these distributions. For example, for uniform, we have a parameter like A and B, because uniform distribution is between something, between 0 and between A and B. Remember in that example of a spinning wheel pointer, that the area around the circle was, for example, 1. So when you turn randomly, this pointer is going to stay somewhere between 0 and 1, but equally. So the chance is equally to stay in any of these parts. So we're going to see that. We're going to talk about something new today called exponential distribution. Of course, it's exponential. Exponential is very important. We can see that. There is another parameter for this, is lambda, that is rate. And we have Gaussian. Gaussian is the main distribution that we're going to study in this class, because so many phenomenon in this world consider Gaussian. The reason is that Gaussian calculation coming from adding on, like infinite random variables that we don't know what is their distribution. When we add them together, it becomes Gaussian. It's called what is called? Yeah, it's called a total theorem. That when you're adding so many phenomena that you don't know their distribution, as far as they are independent, if you add them all together, it becomes Gaussian. So we're going to see that. Yeah, so let's get started. First, we start with uniform. We already talked about uniform a lot, but the discrete form, not continuous. So the continuous form is, the example of continuous form is that a spinning wheel pointer. So again, always try to remember that. Anytime we want to switch from continuous, from discrete to continuous, just remind that you have this spinning wheel and a pointer here, that this pointer is turning randomly, but this area is one limited size, for example, here is between 0 and 1, 0 and 1, but can be between A and B, for example. So in this example, I consider A and B. So when we turn randomly, can stay in any of these portions, any of these sections, and the probability is equal. If those portions are equal size, probability of staying in 1 is same as all. And when we go from n, and when we limit n to infinity, it still is the same way, but we are moving from discrete to random. In that case, that distribution, when n going to infinity, called continuous uniform random variables. For continuous, we have PDF, and PDF is 1 over b minus a. If we draw that, PDF x between a and b is like this. Okay? So that's, and the integral, for example, you want to see, here is, I don't know, 2, for example. You want to see what is the probability, maybe if it's between 0 and 1. In this example, let's consider, for example, 0.6. If it's between 0.6 and 0.7, for example, what is the probability? 6, 7. Between 0, 6, and 7 is the area, that area. We need to compute that area. That's going to get us probability to being in this interval. OK, so let's do that example that I mentioned, that sometimes f of x can be bigger than 1. OK, let's clean this up. Imagine we are studying uniform 0 and 1. So uniform 0 and 1 has this distribution, 0 and 1. And we have f of x here. And f of x is 1 in this case. So this is 1. As you can see, 1 multiply 1, this area is 1. Now let's study another uniform distribution, another family of uniform distribution with different parameters. In this time, we are actually drawing 0 to 0.5. But f of x is, in this case, is 2. So this a and b changing. So again, if we draw that, this is 0 and 0.5, but this is 2 PDF. Again, when we multiply them together, the area, actually the integral between 0 to 0.5 of this f of x is 1. So that's the case that's happening. So the area is different than adding those f of x, because we always need to multiply them with delta x that's going to 0. That makes it very little. So that's different between integral and summation. OK. So let's go back to our uniform distribution between a and b. This too was the reason that I wanted to mention sometimes f of x can be bigger than 1, but the integral going to be still 1. The integral of that portion or part or section. OK? So what we can say about uniform between A and B always bigger than A, of course. What else we can say? We can say they are in all interval, they have equal probability. That's normal. And it's a flat distribution. And represent maximum uncertainty on a bounded interval. Okay, so that's something. What other property that we can say about this uniform random variable? Expected value. So what was expected value coming from? Expected value was the integral between A and B. If you compute that, I'm just going to write the formula. Expected value was the integral x, f of x, between A and B. Okay, because the rest is 0, so we don't need to consider that. And this is going to be, if you put x, a, b, 1 over b minus a, and compute this integral, is going to be this. I'm not going to do the rest. What about variance? Variance is also, we know, the variance of x is equal to expected value of x squared minus expected value of x, all of that square. So if we compute that, first we need to compute this part. Instead of this x, you need to put x squared and get integral. And eliminate these two together, and it's going to be this. I'm not going to go there. But this one is important. What about CDF? Okay, we already have PDF. We know PDF coming from derivative of CDF, and CDF coming from integral of PDF. But we need to consider f of x is the integral from minus infinity to x. This is the important part of f of x, x. Okay, this is important. It's not from plus infinity to the x, because it's cumulative. This is CDF. Okay? So if we do that, let's see how we can find f of x is integral between a and x, 1 over b minus a, d of x, and this is going to be it's just constant. It's going to be x minus a over b minus a. Okay, so that formula coming from here after computing this integral. Okay, any question? This uniform distribution is one of the simplest distribution you're going to see in your life. But still, you need to compute this stuff. You need to know this formula. You need to know expected value, variance, and how we are switching from PDF to CDF and vice versa. You need to know that. Let's do one little example here. Imagine we have a uniform distribution between 0 and 2p, like an angle. So the angle theta is between 0 and 2p, is like this. Instead of having that distance, we are considering this theta, okay? So it's always need to visualize things. So visualization is very important to understand topics. Anyway, so based off this formula, expected value, and first of all, a PDF is 1 over b minus a. b minus a is 2p minus 0 is 2p, so 1 over 2p. between 0 and 2p. Other than that is just 0. We don't need to write it. Expected value, if we put there this formula here, is going to be p, and variance is going to be pi squared over 3. Okay? That was a little example showing how this uniform distribution works. And for angles, that also works. Okay. Let's go for, because we had lots of, we talk about uniform is enough. We need to go to another one. Another family of random variables that are very important and we need to study in this step is exponential random variables. Exponential random variables have this PDF probability density function that is exponential, of course, and it has one parameter, this lambda, one parameter. That is parameter is called rate. It's called rate. We can see why it's called rate. CDF of that, so how we can find CDF, we just need to get integral. Integral of that is going to be this one. So we're going to just very fast compute the integral. CDF is equal to integral between minus infinity to x. But here we don't have minus infinity. We have 0 to x. F of x d of x. So is equal to, if we put that, we can take the lambda out, 0 to x, e minus lambda x. So what happened? Yeah, I need to write here. No, please. Wire is not enough. Okay. Keep. What happened? Yeah, sorry. Okay, came back. So this and the integral of that is equal to lambda. Integral of this is 1 over lambda minus e minus lambda x, x and 0. If we put that there, this is going to be in overall 1 minus e lambda x. Okay, so CDF going to be this one. Okay. So I don't want to teach you integral, but you need to know these little things in your exams or quiz, whatever, in your real, problem solving, whatever you want to do. Sometimes you need to deal with these little integrals as well. Okay, so if we draw PDF, let I clean this up. Okay, I can clean the rest. Anyway, this is the PDF, and CDF is like that. Exponential, and this is also increasingly, but it's still growing exponential. So many phenomena happening like that, including the time for like a first success, or yeah, we can see an example. So key interpretation. This is modeling waiting time, can be modeled waiting time until first event. Is that familiar? Waiting time until first event. In discrete form, we had another distribution that explained this. What was that? Any guess? Do you remember one distribution that explained waiting time until first event? Bernoulli. The Bernoulli was one time, but when we repeat it, but the Bernoulli was different. This is the waiting time. No, it's any other idea? No, it's not a Poisson. Any other?
Geometric.
Geometric. Yes, it's geometric. Geometric distribution explain the waiting time between, until the first event happened. Remember, we said, okay, we are repeating, for example, dice, for example, dropping the dice, and to see, or coin. For coin is easier. So we are how many time we drop the coin to first head coming, for example, something like that. So in that case, we had discrete form. But what about if we have continuous form? In continuous form, the exponential family can explain this phenomenon, waiting time until first event. Why? This is relationship between exponential and geometric, because these two are kind of a limit of each other, like exponential family is the continuous time limit of geometric distribution. This is very important part. If you write the formula, you can write limit of 1 minus x and n, when n go to infinity, is e minus x. This is the formula. So as you can see, when we get limit, this is geometric. And when we get limit, it's going to get equal to exponential. That's a relationship between geometric distribution and exponential distribution. Okay? So that's great. So we have something to explain this waiting time happening a lot and a lot in our job, because sometimes we want to use for calling, networking, failure time, arrival times, anything related to time. In discrete format, we were looking for the numbers, but here time. Time and numbers. Time is continuous form of numbers, isn't it? Interesting. So we can see how much this course help us to understand things. Really. If you look at that deeply, you can understand because in reality, so many things happening random with lots of uncertainty. And if you can model this uncertainty, you can understand the world easier and better. And all of these scientists that created this stuff, they all wanted to understand the universe or world or these uncertainty things that are happening in the world. Are you following, you guys, what I'm talking? I'm talking about universe. It's very important stuff, okay? No, really, it's very important. And if you can understand these things, it's going to make understanding other things easier too. Okay, anyway, let's go. Important properties. So for random, exponential random variable, expected value is 1 over lambda. Variance is 1 over lambda square. And the standard deviation is actually a squared of variance. maybe I didn't explain that before, but is when you get a square root of this, it's going to be 1 over lambda. That is a standard deviation. That's a standard deviation. That's variance. Okay? Oh, I forgot the important one, this one. That's very important. So I'm not going to compute this stuff. You just know formula and integral and differentiation of exponential family is very easy because it's equal to itself. If there is some parameters, you can put that out, but that's it. So let's go for this formula. This is very important part, memoryless property. Oh, wow. Let's see, have time for that. Let's clean this up. Some distributions or some type of random variables, some family of random variables, we call them memoryless. They don't have memory. It means what happened later is not dependent on past. This kind of phenomenon are easier to model. Imagine you want to make a decision. You don't look at the past. You just make decision based off now. This kind of phenomenon called memoryless. Later on, we can also call them Markov models. Later, we can see that when we study Markov models. It's very important for dynamic, for motion planning, for robotics. We use them to make everything simple for us. But we also can see this phenomenon, this memoryless property happening in exponential family because of exponential mathematical formulation. So, so what that means? If we say one distribution is memoryless, we are talking about time. When we want to talk about memory, we are talking about time. We are saying, okay, probability of something like x happen bigger than s plus t if x is bigger than s. Okay, so we are talking about time. We have s here before t, and x is even after t. So we are talking about x, but we had two previous actions, s and t. Okay, we are saying probability of x happening, that this probability of this, if we had these two things happening, if we know x is already bigger than s, and we add this s with a little t, it's not dependent on s anymore. It's just dependent on t. So it's px bigger than t. We are just eliminating previous actions. Why this is true for exponential family? Because we just need to write the formula. If we write the formula of this, like x given y, for example, it was probability of x and y, but probability of x and y, because this is part of that, is also equal to probability of x bigger than s plus t over probability of x bigger than s. And we have this one. This is e minus lambda s plus t. And this is e minus lambda x. When we divide them together, it's going to be e minus lambda t. E minus t is actually p of x bigger than t. This is the proof of that, but you don't need to know all the details for this. But this can compute it with the formula for P of A given B is equal to P A and B, P of B. That's why it's memoryless. We're going to work with memoryless a lot later. But here we just need to consider that this exponential family is very good a probability for studying. And we can see the application in anything related to time. A duration time, calling time, failure time, you know. Okay, let's do example. One good example is call duration. You consider call duration exponential family, and the rate is 1/3. It's probably minutes. So it means expected value, because we know expected value of x is in exponential family is 1/λ is 3 minutes, for example. So imagine the expected value, the average call is 3 minutes. Of course, it's not 3 seconds. It's more than, okay. We consider the average 3 minutes in this example. Okay, so we have this. What we were asked, what about find the probability that probability a call lasts between 2 and 4 minutes. So what we want to find, probability of t, it's t, it's not x. Okay, so I just changed this to t. Okay. Probability t between, why my computer becomes slow? Okay. T between 2 and 4. Okay. So how we can compute that? This can be computed from CDF. CDF of 4 minus CDF of 2. Okay? And what was CDF? We had CDF. F of x is 1/e minus lambda x. Remember, we had that. So we just need to put that formula and compute that. If we compute that, the result's going to be something like this. Okay, even you can compute that with numbers. You need to use calculator, of course, for that. And what about expected value? As I explained, is 3 minutes, and variance is 1/λ square. If you do that, it's going to be 9. Okay, so that gives you some information about this example. So the expected value was 3 minutes, and probability of calling between 2 minutes to 4 minutes is 0.25. Okay, this is some kind of information that you can get from that, and the variance is 9. So what is variance? Variance showing how we are varying around mean. The mean is 3, so we are varying this time around mean. It's lots of variance. Too much. Okay? And standard deviation is a square root of variance, that is 3. Okay, so that was actually exponential family. Let's go to the Gaussian. Gaussian is the most important distribution that we're going to learn in this class. Everything using Gaussian makes everything easier. So what is a story behind Gaussian? So of course, in that time, 1800, all, maybe not all, most of scientists and people were thinking about understanding like volt, how volt working, how they can understand it better. And always they were connecting this life and universe to outside. They were looking at stars to find the reason. And makes sense. They haven't had enough knowledge or whatever to see some reasons inside the world. They were looking outside to find the reason of the world, whatever. And Gauss was one of them. And in that time, they were trying to measure the distance between planets. Wow, that's complex. Because planets are moving, and they wanted to measure the distance between them. They wanted to see if this distance equal all the time, or they are expanding or shrinking, whatever. And they couldn't, because it was so many things involved. The result was very off all the time, and the measuring that was very difficult. The reason was because in that time, the instruments that they were using they were very imperfect. And of course, we had some human error. We had some, the distortion, like atmospheric distortion, like cloudy, whatever. And these things were always happen. That so many mathematicians or scientists, they were trying to model that because they were thinking something there that we need to understand to maybe understand the reason of the world or life, whatever. But they had some similar stuff. These errors that happened, always they were small errors. They were not big errors. The big errors were rare. They were small. And also they were symmetric. Errors were symmetric. Like, it means the positive and negative, like, equally likely. So they were kind of following a bell shape. If you consider here negative error and here positive error, they were symmetric. So it means, for example, error minus 0.7, the probability of that was the probability or PDF of that, because it's continuous, was equal to +1. However, when I'm talking +1, it means around +1. Of course, we can have 1 or exact value because it's continuous. Anyway, this was the thing at that time they were working on. They were working about this part of modeling the world that, of course, was random. And in that time, Carl Friedrich Gauss, in 1800, between 17 to 1800, studied this measurements error, because this measurements error coming from so many reasons, as we just called 3 of them, but there should be a million other things, because all of those are related to so many things. Like a human error, coming from all the evolution that happened for us. These errors that happen for our understanding of the world coming from other stuff. The history that we had behind us let us, for example, our eyes work like this. So many reasons. Okay? And other stuff too, like instrument imperfection. The telescope that they were, that's so many reasons we can find for that. And they are just add of all of them. And in that time, Gauss found out that these errors are random, of course, and the positive and negative are equally likely, and a small deviation are more happening, around the mean. And a small deviation are more common than large deviation, of course. So it means the probability to be close to the mean is higher. So he created a function that can explain this curve. And that's called actually Gauss formula and the Gauss distribution later on. In this family of random variables, you have 2 variables, 2 parameters, sigma and mu, that we're going to see them later. So that was the reason of creating this. But right now, that become like a basic of so many other applications, like machine learning, and perception, robotic perception. We call it probabilistic perception in that sense. And so many other phenomena that can model the world. Okay, but what is coming from? It's coming from this idea, central limit theorem. Central limit theorem, we can prove that, but it's not time today for that. Maybe another time we get the chance to do that. Central limit theorem is kind of explaining so many things around the world. It's explaining if something happening a lot and independently, if we add them together, so imagine you have n different phenomena that they are, independently can happen, and you add them together. If you add them together, whatever distribution they had, the sum of them tend to follow Gaussian distribution. Wow, that's very big notes that I wrote here. You can model it a lot. Imagine you are in a beach, and you are collecting some rocks. And you drop the rocks in top of each other. The rocks have different shape and distribution. Some of them flat, some of them round, some of them very rough. Doesn't matter, they had different distribution, but you drop them in top of each other. Maybe the first one and second one not following any distribution, but imagine you collect millions of them together. What shape gonna look like? The curvy bell shape, isn't it? That's very simple intuition of this central limit theorem works. So when we add them together, all of those uncertainty and whatever, smoothness or roughness of those rocks that coming from distribution of them get disappear because they cancel out each other, and the overall becomes something that we call it Gaussian distribution. And Gaussian distribution is a type of distribution that can use for measurement noise, because measurement noise coming from millions of other factors. Communication systems noise also the same. Biology, like height, for example, is coming from so many reasons. You can't find a reason to height of men be in this size. There's millions of reasons for that. You can't find all of them, but you can say the overall, they're following normal distribution. Also, we call it normal distribution. Normal or Gaussian, same. Okay? Estimation, finance. And anytime you don't have, anytime you have so many factors for some phenomenon, you can consider that phenomenon Gaussian, if there is so many factors for that. Okay? It's not magic. It's mathematics. That's a very good point. Okay, let's go see this formula for Gaussian and a little study Gaussian and finish it for today. So as we mentioned, for measurement noise, for natural phenomenon, for communication system, for estimation, this is whatever you're going to see in your career. All of those things that I mentioned. Measurements, noise, natural phenomenon. When you want to model each of these, you need to consider this normal or Gaussian happening. What is the definition? The Gaussian distribution has this formula. As you can see, it's a kind of exponential. But in exponential family, we had exp of x minus, exponential of minus x, lambda minus x, something like that. but here we have exponential of something like lambda prime x squared. So that's a little different, you know. But it's still a little similar pattern. And this square led them to become symmetric. Exponential was like that. It wasn't symmetric. Okay. I just want to mention that they are different. They are not similar. Okay? So that's how we can explain it. This sigma is a standard deviation, of course, and sigma squared is a variance, and the mu is another parameter that is mean. So it's very interesting. You just need two parameters to explain this distribution. Two parameters, and those parameters has meaning. Mu is the mean. When we are eliminating x from mu, it means x is symmetric around mean. As you can see, this x is, the mean is here is 2, I think. Yes, mean is, mu is 2. And x is around that symmetrically, is symmetric. Okay, this is coming, makes it symmetric. Okay, because the minus x and plus x is not changing. That square gonna fix it. Okay, this is normal distribution. You don't need to remember, like memorize this formula, but you need to understand it where we have the minus, when we have a square. Some notations that we are using for squares is like that. When we are saying x is following, this is showing following normal distribution with two parameters, mu and sigma square. Mu is mean and variance. Okay? Property, so mu and variance is this, is symmetric, and the total under that is always 1. This is always 1. And bell shape. Okay, any question? We will work with Gaussian a lot, so we're going to learn that more. But let's do example. A simple example is height. Imagine you are studying height of people, and you got some measurements, and we know the height is following normal distribution. Makes sense. As I mentioned, so many biological things like height is coming from so many other things, so many other reasons. Some of them coming from the environment, some of them coming from your genes, some of them coming from your, so many other factors. Food that you are eating, whatever, and all of history behind it, and evolution. So lots of reasons. That's why this is a normal distribution or Gaussian distribution. And we want to see what is the probability that somebody's height is between 1 meter and 90 or 190 centimeters to 200 centimeters. Okay? We want to measure this probability. So we can compute this probability because it's between these two. It's an interval. Probability of interval is always exists. Probability of x between 190 to 200 is equal to the integral of PDF. And integral of PDF is going to be CDF, so we can write directly CDF, that is capital F, f of x 200 minus f of x 190. Okay, that's a CDF. CDF. Okay, so we know that. What else we need to know? We need to know these parameters. We know the average is 175, and the standard deviation is 7 centimeters. So variance is 7 square, of course. So that's the formula. But we don't need to compute this formula. There is a Python code or MATLAB that you can use, norm CDF. This is going to give you the value of CDF. But probably your calculator also can compute that too. I'm not sure if it's advanced. So it's going to give you the CDF. So the probability coming from that formula that I wrote, probability for 200 minus probability 190 with those two parameters, and print it out. Any question about this? If you draw that, this is the PDF. And as you can see, the average is here, 175. And the probability of being 190 to 200 is very little. This area that is shaded, this green area, when we compute that, I don't know if I have the result. Unfortunately, I didn't write the result. But it's going to be very little. So it means, because it's very far the average is 175, and this is very in a tail, so it's very low. But this is the area under that. That's why it's coming from this integral. Any question about this? Good. OK, so in MATLAB also you have something similar. A function, probably it's called CDF. And you have same parameters. You give mu and sigma, of course, and that's x that you want to compute. OK, so I'm not going to continue this first. If you have any other questions about this random variable, Gaussian random variable, let me know. OK, so we're going to finish it a little earlier today. So what else we have? Actually, I wanted to remind you, you have assignment that due date is, it was Saturday. I moved it to Friday. I appreciate it. I know you're going to leave it in the last minute to do it, but try to do it as soon as possible. Don't leave it to the last day, because I wanted you to have more fun for your spring break. OK, have a great spring break. See you after that.
Make sure you also
exam. It's not going to be the exact after. Yes. I will let you know.
Well, I don't think so. His classmate now. Yeah.
Yes. It's not exactly. I consider the duration of 2 weeks. I'm going to put it in the last day of 2 weeks. Add more stuff. Yes, sure. But I'm going to let you know, of course.
Like,
before.
So I'm used to this.
I think so, yeah. Yes. Yeah, it should have some overlap, of course. Yes, yes. Sorry about that.
It's like double the amount of snow.
I just disconnect this thing. I don't want to record that. Yes, you can.
We'll be at the Exponential. And last Friday. I don't know why.
half hour.
Oh, okay.
Like similar, but not really. Okay.
You want to do it now? Okay, so do you want to? Do you have time?